So here's a super quick rundown for Biweekly 106 that just ended 19 minutes ago. I did pretty good. I got 403. I made a really stupid 2 errors on problem 1. So speaking of which, problem 1, it says a number is fascinating if when we append 2 times the number and 3 times the number as a string, when we concatenate them, the number will have all the numbers 1 through 9 and not 0. So, for example, 192 is true because 192 times 2 is 384, times 3 is 576. So then we get 192, 384, 576. That's all the numbers 1 through 9 and not 0. So that's pretty much what I do. I just say, okay, well, build the string. If there's 9 numbers in it and none of them are 0, and also it's 9 numbers long, and there's 9 distinct numbers, then we're good to go. One of the errors I made was just like that, which is really stupid. It's a string, so you have to do like string 0, not number 0. Another one was originally I didn't have that because I was just like dumb and I didn't realize, 999 times 3 and 999 times 2, if you concatenate those, it's just longer than 9 numbers. That's the answer to this one. Longest semi-repetitive substring. So this one, a semi-repetitive substring is a substring where there's 1 repetition. So like 5223 is 1, and so on. So what did I do? I forget. Oh, the immediate thing I saw was, well, s.length is less than or equal to 50, so we can kind of do whatever we want. There's probably a way to do this in linear time, but who cares? So I just said, okay, take every single substring. If it's semi-repetitive, then see if its length is longer than our current maximum length. And then the end, just return the maximum length of all of these semi-repetitive things. So then the check function checks to see if it's semi-repetitive. So we say, have we found a repetition? Go through. If there's any element that's the same as the previous element, then we've found a repetition. So if we've already found one, then no, this isn't semi-repetitive because now there's 2 repetitions and we only allow for 1. But if we haven't found it, then now we've found this one. And then in the end, just return true if we can get all the way through the substring. So it's O of n cubed, right? Because you have these 2 pointers that are iterating through O of n, and then also you're checking O of n here, but I mean, whatever. That's why that one's the second question and not the third or the fourth. So movement of robots, if you want to pause and read it, it's pretty long. But the idea is we have all these robots that have starting positions, and then they're moving in a given direction, and then there's a certain amount of time that's passed, and we want to know not only where are all the robots, but also how far away are all of them from all of each other. And we can immediately see it's going to be very large because they're busting out the modulo 10 to the 9th plus 7 thing. This is definitely a question that encourages you to just reread the question a bunch of times, because like an initial thought you might have is, what happens if you have a robot, like, okay, here's 0, 2, or that's not a great example, -2, 0. But say we have like a robot that's at 0 and a robot that's at 2, and they're going in this direction. They're going here. So they're both going to intersect at 1. But what happens? Do they just occupy the same spot for the same amount of time? Yes, they do. So they'll both be here at time step 1, and then they'll both keep going. Or I'm sorry, actually, they won't keep going. They'll both bounce off each other. And then we'll have a robot at node 0 and a robot at node 2 going the other way now. But then what happens if it's like node 0 and node 1? In that situation, do they just pass through each other? Do they bounce off? Because like this should be going to node 0 in the next time step if there was no other robots. This should be going to node 1 in the next time step if there's no other robots. And the moment you ask that question, you realize like it's the same thing. It's the same thing here at least, because here what you're going to get, what would it mean for them to bounce off of each other? That would mean that I guess this bounces off and then it's at node 1 again, and this bounces off and it's at node 0 again. So we have something like this. But what does it mean if they don't bounce off of each other and they go through each other at even indices? Well, that would mean that this keeps going to node 1 and this keeps going to node 0. So it's the exact same state. I should flip these around to make it less confusing. It's the exact same state regardless of whether they bounce off or not. And it's the same thing with here. this is also the same state. When they intersect at node 1, whether they pass through each other or they bounce off, it's kind of the same thing because we don't really care which robot is which. If we did, then it would be different if they had some color designation or something. But they don't, so who cares? So once you realize that, that's like the big crux of this problem, is to realize, like, I mean, it's an observation check. It's a matter of deduction to just be like, well, this whole thing doesn't matter. This could be a huge fiasco. You could have some giant monotonic stack thing, maybe. But just don't even do that. The first thing you want to do is just be like, if it's going right, move it right by D places. If it's going left, move it left by D places. And then once you have that, then it's just a question of, well, you have this updated nums array. How do you find the sum of differences between all elements? That's kind of a common thing. It's not super common, but you sort of just iterate up or down. I literally just copy pasted this from Geeks for Geeks. It's like, just how do you find all, like how do you find all the prime factors of a number? Like, I don't know, copy paste it from something because it's faster than like writing it out yourself. At first I wrote it out myself and it had a little typo error that I couldn't find. So that was the third error I had. And then once you have that, you're good to go. It's just a matter of realizing like them bouncing off of each other and them going through each other is the same thing. And then once you have that, it's just a pretty well-known problem of what's the sum of differences between all elements in an array. Okay, so Q4, find a good subset of the matrix. This is similar. You can pause to read it. But this is similar in that it's kind of a matter of deduction. You kind of have to think and be like, how could we possibly know the number K? And my thought process was, what if you binary searched? Which doesn't really mean anything, right? Because then you're optimizing, but we could have any K. So the moment we find any K that works, we're good to go. But say you did binary search. Say you said, I want to look for exactly when K equals, let's say, the length of grid. Let's say if you include every single row in the length in grid, what happens then? Like, is there a quality of monotonicity to this where I can say this did work, therefore K over 2 will work, or this didn't work, therefore K plus 1 won't work, something like that. And it turns out, like, yeah, there is. Like, specifically when K equals 1, you have this weird corner case where there could be a row that's just all zeros. But other than that, there's no way you can ever get K equals 1. Like 0, 0, 0, 1, you can't have a subset of just that because you have this 1 here. The only situation where you can have that is if it's like 0, 0, 0, 0. Then you could have K equals 1. So other than that specific corner case, if you think about it, like, there is this quality of monotonicity that would allow you to binary search if there was a different optimization question being asked, which there's not. But the point is, like, there is this quality of monotonicity, as in if a subset of length K works, a subset of length K minus 1 would also work, all the way down to 2. And kind of what that comes down to is this proof that it's a little shaky in my head. I think there's like 4 or 5 different ways to phrase it, but I'm just going to write it with text. If you have, like, this is your grid and these are all your rows, if you have something like this, the only situation that would allow you, or let's say something like this, the only thing that would allow you to have a feasible subset that includes this is if there's another subset that doesn't include all of these, that doesn't include the same one. So you have to have either that, that, or that, or that, I guess. Or also the last one, just to be comprehensive, would be that. You need one of these 4 in order to ever complete any subset that would contain this. Because, like, if you had a subset that was like, okay, we have that, we have 0, 1, 1, 0. Okay, well, now we have this overlap here. So the next thing can't have that. If we're saying this is our subset, what if we had like 1, 1, 0, 0? Well, that suddenly also doesn't work, actually. But we would need the last one would have to be 1, 0, 0, 1. And now, because we've done this like stair pattern where we've been like the last two, the second to last two, the third to last two, the fourth to last two, now it'll work because every row has a sum of 2, right? We can see the staircase effect in action. But the thing to realize, and like this was the thing that I just spent, I think like a good 10 minutes just pondering before like submitting, which I should have just submitted and gotten the wrong answer or risked it, which I wouldn't have gotten. The thing to realize is that like there's no stair configuration that will ever work that doesn't involve just like that. So in that world, you can just be like, okay, goodbye to these two. I don't care. K equals 2. It's that. And you could do the opposite too. You could be like, well, you know, similarly, because this is here, we don't really care about these ones. K equals 2. It's this. So with that in mind, we can use this big hint that they gave us, which is that the number of columns doesn't exceed 5. They could have had this be a lot less stringent. They could have had this be like 20. But the number of columns doesn't exceed 5, which strongly implies that they want you to use some sort of backtracking through the columns or permutations of columns, or in this case, bitmask DP. That's like the thing to do, bitmask DP, to just be like, represent each row, which is a binary array, represent that row as a number. So 0 in the 1's place, 1 in the 2's place, 1 in the 4's place, 0 in the 8's place. That's a 6. Or you could go opposite, it doesn't matter, but we'll say 6. This would be 8, because like 0, 0, 0, 1. Or this would be 15. And then you represent them and you say, have I seen this row? Immediately, if I've seen this row, I don't care. Just skip it, because I've already deduced that it's not possible, or I already have it recorded for something later. So I'm getting a little ahead of myself. The first thing we do is we create the bit mask, quote unquote. So if we say print mask, we can see what it'll do for that first situation is say, oh, hey, print a 6, print an 8. And then we don't print the 15 because we actually already found something that works. So we already like cut out early. But we say, okay, have we already seen this number? If so, continue, because we could just use that number instead of this if k only equals 2. We never really ever want any repeat numbers. And then if the number itself is 0, then we just return that one index. K is 1 and it's that. If it's not 0, or I'm sorry, if this isn't the first number that we've seen, which I don't think you really need this, look through everything we've seen and say, are they mutually exclusive? AKA, if not x, for x and everything that we've seen, and mask. So x and mask will be the bitwise and operation. So for example, like 0, 1, 1, 0 and 1, 1, 1, 1, if we're representing these as integers, will be 0, 1, 1, 0. It'll only be the spots where both of them are 1s. But 0, 1, 1, 0 and 0, 0, 0, 1, all the spots where these are 1s, these are 0s. And the spot where this is a 1, this is a 0. So this and this will return 0, which necessarily means that all the spots where this is a 1, this is a 0, all the spots where this is a 0, this is a 1, aka they're complementary. They don't share any 1s or 0s, which means if we take both of these as our subset, then we'll never exceed a sum of 1. And since k is 2, we're allowed a sum of 1. So here, like the sum for the first column will be 0, and then 1, and then 1, and then 1. So that works. So we look, we're like, okay, we've seen 6, 8, compare it to 6. Oh, it works. Return 0 and 1. And then if we get through the entire thing and we don't find any good fits, then just return nothing. And this is O of n, or m, sorry, which is 10 to the 4th, which is fine. Because we're just throwing all these masks that we have into a scene dictionary. And then since it's a dictionary and not a set, because we have to keep track of the original index. Yeah, that's that one. I think it's another kind of observation one to realize that k can never exceed 2, which is kind of fun and interesting to think about. So yeah, that was this contest.